A voltage regulator is a device designed to maintain a constant voltage output, irrespective of variations in the input voltage. It achieves this by employing feedback mechanisms that adjust the output voltage to align with a predetermined reference value. The operational principle of most voltage regulators hinges on switching. They incorporate a power transistor or MOSFET to facilitate the rapid switching of the power supply on and off. By meticulously controlling the duty cycle of this switching action, the average output voltage can be precisely adjusted. The internal connections of a voltage regulator can vary significantly, contingent upon the specific design. However, they generally encompass several key components. Firstly, input terminals, which serve as the conduits for connecting the input power source to the voltage regulator. Secondly, output terminals, responsible for delivering the regulated output voltage. Thirdly, feedback resistors, which generate a reference voltage utilized to govern the output voltage. Fourthly, a control circuit. This crucial element monitors the output voltage and dynamically adjusts the switching duty cycle to sustain the desired output voltage level. Compatibility between a voltage regulator designed for a three-phase system and a two-phase system is not guaranteed. There are several reasons for this incompatibility. One is phase mismatch. A three-phase voltage regulator is engineered to receive three distinct input phases. Conversely, a two-phase system only provides two phases. This discrepancy can lead to complications within the feedback mechanism, which relies on the intricate phase relationship between the input and output voltages for proper operation. 2 is reduced output capacity. A voltage regulator tailored for a three-phase system may not be capable of delivering its rated output capacity when connected to a two-phase system. This limitation arises because the voltage regulator leverages the phase diversity inherent in a three-phase system to mitigate current harmonics and optimize performance. In conclusion, it is generally not advisable to employ a voltage regulator designed for a three-phase system within a two-phase system. While it might appear feasible under certain circumstances, there exists a substantial risk of diminished output capacity, compromised regulation accuracy, and potential damage to the voltage regulator itself. It is invariably recommended to opt for a voltage regulator explicitly designed and certified for compatibility with the specific type of power system in use. When evaluating voltage regulators, several key specifications and features should be considered to ensure optimal performance and compatibility with your specific application. Firstly, input voltage range. It is crucial to verify that the voltage regulator's input voltage range aligns with the voltage levels present in your power system. Select a regulator that can accommodate the expected variations in input voltage without compromising regulation accuracy. Secondly, output voltage and current. Determine the required output voltage and maximum current demand of your load. Choose a voltage regulator that can provide the necessary voltage and current levels while maintaining stable regulation under varying load conditions. Thirdly, regulation accuracy. Assess the voltage regulator's ability to maintain a constant output voltage despite changes in input voltage, load current, or temperature. Look for regulators with low voltage drift and high line and load regulation specifications. Fourthly, protection features. Prioritize voltage regulators that incorporate comprehensive protection features, such as overvoltage protection, overcurrent protection, short-circuit protection, and thermal shutdown. These features safeguard the regulator and connected equipment from potential damage due to abnormal operating conditions. Fifthly, efficiency. Evaluate the voltage regulator's efficiency, which is the ratio of output power to input power. Higher efficiency translates to reduced power dissipation, lower operating temperatures, and improved overall system performance. Sixthly, switching frequency. Consider the switching frequency of switching voltage regulators. Higher switching frequencies enable the use of smaller and lighter components, but they may also lead to increased switching losses. Choose a switching frequency that balances size, efficiency, and cost considerations. Seventhly, ripple and noise. Assess the ripple and noise characteristics of the voltage regulator's output voltage. Lower ripple and noise levels are crucial for sensitive electronic circuits that require a clean and stable power supply. Eighthly, transient response. Evaluate the voltage regulator's ability to respond quickly and accurately to sudden changes in load current. A fast transient response ensures stable voltage regulation during dynamic load conditions. Ninthly, operating temperature range. Verify that the voltage regulator's operating temperature range aligns with environmental conditions of your application. Choose a regulator that can operate reliably within the expected temperature range without dirtying its performance. 10thly, safety certifications. Ensure that the voltage regulator complies with relevant safety standards and certifications such as ULC and RoHS. Compliance with these standards ensures that the regulator has been tested and certified for safe operation. Internal connections of voltage regulators also include capacitors, inductors, and diodes. Capacitors are used for filtering and energy storage, inductors are used for energy storage and current smoothing, and diodes are used for rectification and voltage clamping. Different types of voltage regulators include linear regulators, switching regulators, and servo voltage regulators. Linear regulators are simple and inexpensive, but they are not very efficient. Switching regulators are more complex and expensive, but they are more efficient. Servo voltage regulators are very accurate, but they are also very expensive. The choice of voltage regulator depends on the specific application. For example, a linear regulator might be suitable for a low-power application where efficiency is not critical. A switching regulator might be suitable for a high-power application where efficiency is important. A servo voltage regulator might be suitable for an application where high accuracy is required. The selection of a voltage regulator for a specific application requires careful consideration of various factors, including input voltage range, output voltage and current requirements, regulation accuracy, protection features, efficiency, switching frequency, ripple and noise, transient response, operating temperature range, and safety certifications. By thoroughly evaluating these specifications and features, you can choose a voltage regulator that meets the specific needs of your application and ensures reliable and stable voltage regulation.